Let's start miles below the surface. The Mediterranean basin sits right where the African and Eurasian tectonic plates collide. Specifically, the Ionian subduction zone is rolling back to the southeast. As this plate sinks and pulls away, it stretches the continental crust behind it. This process, called back arc extension, stretches the crust until it becomes incredibly thin. That thinned crust acts like a pressure release valve. Magma surges upward, creating a highly active volcanic landscape that remains almost entirely hidden beneath the water column. When we think of Mediterranean volcanoes, we picture land-based giants like Mount Etna, visibly smoking over populated cities. We can see the threat. But the region's most significant geohazards are not the peaks we can see against the skyline. They are the massive, structurally complex, silent giants hidden offshore, and right now they are vastly undermonitored. The primary danger of these submarine volcanoes isn't an eruption of lava, it's the water they displace. A massive mechanical flank collapse or a shallow hydrothermal explosion can trigger a rapid onset tsunami. And because these structures are located so close to the coastlines, the time constraint is extreme. Regional arrival times for these tsunamis are typically between just 10 and 30 minutes. Our traditional land-based seismic monitoring networks simply weren't built for this. By the time a shoreside seismometer detects an offshore collapse, the wave is already moving toward the beach. To mitigate this blind spot, we have to dissect the three distinct mechanical failure modes of the Mediterranean's volcanoes, and we have to completely rethink our deep-sea observational architecture. Our first case study is the Marsili Seamount in the Tyrrhenian Basin. Unlike a classic cone volcano, Marsili is an elongated ridge built on a critically thin section of crust that is only 10 kilometers thick. This diagram shows the true scale of Marsili compared to Mount Etna. Marsili is 70 kilometers long and rises 3,000 meters from the seafloor. It is an immense volume of rock. At the very top of this ridge, we find continuous high-temperature hydrothermal fluid emissions venting directly into the seawater. These superheated fluids don't just vent out, they penetrate the rock itself. Through a process called hydrothermal alteration, the fluids dissolve the rigid mineral structures and deposit metallic sulfides into the basalt. This chemical reaction actively degrades the basalt. Over time, what was once solid volcanic rock turns into low-density, highly fragile zones spanning the entire summit. The worst-case failure scenario triggered by this weakness is mechanical. A massive section of the flank simply detaches and slides into the basin. That sudden displacement of water generates a tsunami that immediately propagates outward. The wave strikes the Aeolian Islands in about 10 minutes and reaches the shores of Calabria in 20. Because the rock is already chemically weakened, a massive trigger isn't necessary. A minor regional earthquake or a slight increase in internal magma pressure is enough to cause the collapse. Marsili represents the extreme end of structural instability. It shows how chemical degradation can turn a massive geological feature into a fragile, ticking clock. Now we move to the Hellenic volcanic arc and the densely populated Santorini caldera. In mid-2024, geodetic instruments detected something subtle. The ground across the caldera was slowly inflating. That slow swelling escalated violently in January 2025, when the area was hit by a swarm of over 28,000 earthquakes in a matter of weeks. This 3D model tracks the mechanical cause of those quakes.
300 million cubic meters of magma had accumulated in a shallow reservoir, 3.8 kilometers deep. Instead of erupting upward, the magma punched sideways. It formed a dike that migrated 30 kilometers to the northeast as rebounding pressure waves, seeking neutral buoyancy between 5 and 15 kilometers below the surface.
But as the magma moved, researchers observed a critical anomaly. Both the Santorini caldera and the neighboring submarine volcano, Kolumbo, suddenly began to deflate at the exact same time. By running joint inversions on the data, geophysicists pinpointed how that was physically possible. The model revealed the dike was actually sourced from a shared mid-crustal reservoir located 7.6 kilometers deep, directly beneath Kolumbo. This proves that we can no longer assess neighboring volcanoes as isolated threats. They are mechanically linked, operating as a single, coupled, multi-storage hydraulic system. Our third case study takes us to the Neapolitan area, focusing on the submerged sector of the Campi Flegrei caldera. Here, the threat is driven by Brady seismic, a slow, relentless ground deformation. In just a few years, the ground has uplifted by 1.6 meters, accompanied by intense, shallow earthquakes that literally tear buildings apart. The engine driving this unrest isn't a deep magma chamber. It's a highly pressurized magmatic hydrothermal source located just 2 kilometers below the surface. This high-resolution seismic profile of the Gulf of Pozzuoli reveals how local geology controls this threat. The highlighted, acoustically transparent zones map the exact pathways of fluid migration through the faults. Look at the wavy folds in the rock, the anticlines and synclines. These act as structural traps, catching the ascending gas. As highly pressurized fluids build up, they force their way into the brittle fault lines, triggering shallow earthquakes. The threat at Campi Flegrei isn't a massive collapse like Marsili. It's a persistent, shallow pressurization cycle dictated entirely by local structural trapping. Because Mediterranean geohazards involve deep structural failures and hidden hydraulic networks, relying on surface-level telemetry leaves a critical blind spot in our early warning capabilities. To fix this, the European Multidisciplinary Seafloor and Water Column Observatory, and specifically the Italian INSEE project, are building a monitoring architecture designed for the deep ocean. In the Gulf of Pozzuoli, they've deployed the Medusa infrastructure. This consists of elastic beacon buoys on the surface that are hardwired directly to seafloor deformation platforms, bolted to the seafloor. Further out, they are dropping broadband ocean bottom seismometers to detect deep crustal ruptures. These nodes are built with heavy, sloped casings to protect the delicate instruments from commercial fishing nets. Standardized sensor packages, called EGIM modules, are attached to these platforms, allowing scientists to cross-reference acoustic, thermal, and chemical data across the entire basin in uniform formats. To track deep magma migration and hydrothermal flux, we cannot watch from the shore. We must place instrumentation physically within the harsh, highly pressurized environment of the seafloor itself. But collecting the data on the seafloor introduces the final engineering hurdle. How do you transmit massive amounts of high-resolution telemetry back to warning centers with zero latency? The elegant solution is the Smart Cable Initiative, which stands for Scientific Monitoring and Reliable Telecommunications. Instead of laying dedicated scientific lines, engineers embed environmental sensors, like accelerometers and pressure gauges, directly into commercial telecommunication cable repeater housings. When a tsunami passes overhead, the gauge detects the water column shift, relaying the signal instantly through the fiber optic line. The proof of concept is already active with the INSEE wet demo in the Ionian Sea, and it's scaling up massively with the upcoming 4,000-kilometer Atlantic CAM project. The Mediterranean is not a collection of isolated peaks, but a massive, coupled geodynamic machine. Surviving its inevitable failures depends on a unified fiber optic nervous system wired directly into the seafloor.